Hi, it's Mr. Anderson, and this is Chemistry Essentials video 35. It's on the rate of reactions, or the speed of reactions. Now, some reactions we might think of as incredibly slow. In other words, the rusting of this train car is going to take years and years to occur, to fully complete that reaction, if it ever is completed. But if we wanted to speed that up, we could do it by increasing the surface area of that iron. And we do that in a hand warmer. A hand warmer is essentially a bunch of iron that has been shredded to increase surface area. And so when you pull it out of a bag, it's going to combine with the oxygen and it's going to create a certain amount of heat. And that happens really, really quickly. And so again, the rate of reaction is going to be different for the reactants and the products, but we also have a certain amount of control over that. And so in a chemical reaction, the rate is simply the number of reactants that are converted to products in a given time. And so let's say the red and the blue represent reactants, and we combine those together to make products. The more quickly that we can do that, the faster our reaction rate is going to be. And there are a number of things that are going to affect that. The concentration, in other words, the more reactants we have, the more quickly they're going to find each other, and the faster that reaction is going to occur. And also the pressure. In other words, if we decrease the size of that vessel that they're in, then we're going to have more of those reactions going on. Also, it's going to be the phase that it's in. Clearly, if it's in a gas, in an enclosed container, we might have faster reactions than we would if it's a liquid. And then finally, environmental factors. Things such as temperature and surface area are going to affect the rate of the reaction as well. Now, it's important that you understand what's going on at the molecular level. And so this nice little PHET simulation will help out. And so in this one, the yellow and the other two are going to represent the reactants, and there's products, and reactants and products. In other words, it's converting from reactants to products and back again. Now this is working perfectly because they're lined up perfectly. In other words, every time they hit, there's a perfect reaction. But let me angle that initial shot. Now the reactant doesn't hit the other reactant perfectly, and so we can't convert it to those products. And so it's really important that we're lining them up. And so let me now get a number of those reactions. That was a little bit boring. So let me add a number of different reactants. We're going to call those reactants A. And now let me add a number of different reactants like this. And so you can see by increasing the concentration of those reactants, it's more likely for them to hit each other. But again, we're not getting that reaction occurring because we don't have a high enough energy. So now let me increase the temperature, and you can see that now we're starting to have reactions occur. And if I were to keep track of the amount of those reactants converting into products over time, then I have a pretty good idea of what's going on with the rate of reaction. So what things could affect this? Well, temperature. As we increase the temperature, the molecules are going faster, so they're more likely to run into each other, more likely to have that reaction. If there's more of them, a higher concentration, or if we squeeze them together, if we have a higher pressure, that's going to increase the rate of the reaction as well. And then finally, surface area is incredibly important. All of these are broken down to the level of the atom, but let's say we just had a big tablet filled with A, and it hadn't been broken down, just like that big train car at the beginning. It's going to take a long time for us to break down, and the reactions could only occur on the surface, and that would be a slow rate of reaction.